Welcome back. Our previous video walked through how to do simulated method of moments in Julia. And in this video, I'd like to introduce a different but related estimation technique called indirect inference. Like SMM, indirect inference does not require us to write down a likelihood function, and it is also simulation-based. The main difference between the two is that simulated method of moments uses our structural model to generate moments, whereas indirect inference uses an auxiliary model, which gives a lot more flexibility and a lot more robustness to model misspecification. The main idea with indirect inference is that I just need to be able to capture some key summary statistics about my model, and as long as my model replicates those in the data, then my model is a good model. With simulated method of moments, we're matching model moments to the data and concluding that as long as the model matches the data along these dimensions, then the model is reasonable. And obviously we can harken back to a prior video where we talked about whether fitting on the targeted or the untargeted moments is better. But for now, we'll just leave it like here. And indirect inference offers a different alternative. Namely, it uses an auxiliary model as a lens through which to view the world. And this auxiliary model does not need to accurately describe the true data generating process. It just acts as a lens through which we view the world. And the objective is to choose parameters of the structural model that will make the simulated data and the actual data match through the lens of this auxiliary model. So we can walk through how to do this in the Rust bus engine problem. Let's review what that model looks like. Our main state variable is the mileage of the bus engine. And then we have flow payoffs, which are maintenance costs as a function of mileage and the cost function if I decide to keep driving the bus. Or I have to pay a replacement cost if I choose to replace it, where the replacement cost is some difference between the cost of buying a new engine and the scrap value of the old engine, plus some maintenance cost on a brand new engine. And then we can get this Bellman equation, like we talked about at length several mini-series ago, where we're just trying to choose the optimal sequence of replacement decisions based on our expected value of driving versus replacing, and also how the states evolve over time. So the main challenge with doing indirect inference on a model like the Rust bus engine model is that there's no easy way to invert the auxiliary statistics from the auxiliary model to get the structural parameters. And so we're still going to use this nested fixed point algorithm. We could also consider some other estimation approaches as well, besides a likelihood-based approach. The idea here is that the auxiliary model is much simpler to estimate than the structural model. And so I can use a lot of simultaneous auxiliary statistics. I could look at different moments of the relationship between, what's the average mileage at which a bus is replaced, so on and so forth. And the real power of indirect inference is that the auxiliary model can be misspecified. So the main plus side of having indirect inference is that we don't have to worry about correctly specifying the auxiliary model. The main challenge is that we can't invert this auxiliary model directly to get our structural parameters, which is what we need for policy experiments. So what are the steps that go into this? Well, step one is to choose an auxiliary model. So for the bus engine model, it could just be a simple static logit model where we have the odometer reading on the right-hand side and the replacement decision on the left-hand side. We can get these two parameters on the real data, and then we can consider what we need to have in the simulated data to make that match the real data in terms of those two parameters. So what we're going to do is we have those auxiliary parameters from the actual data. Now we're going to try a guess at the structural parameters, theta, and we're going to simulate the structural model using that guess of parameters. And in the case of the Rust bus engine model, we do have to solve the dynamic programming problem to get the policy functions for that value of theta. And then we're going to have to take those policy functions and use them to generate bus histories while also netting out the state evolution with the odometer readings. And so we have capital S data sets that have been simulated from the policy function and the state variable for our given value of theta, which is the structural parameters. And then once we have those simulated data sets, we can move on to step 3, where we're going to estimate this same auxiliary model on the simulated data. So we run the same logit on all of those, each of those capital S simulated data sets, and we're going to get something called alpha tilde of theta, and we call this the binding function. This is some function that maps the structural parameters into this auxiliary model, and the key issue is that we can't invert this directly, and it doesn't have a closed form, and so we have to simulate for every candidate value of our structural parameters. So once we have that, then we can minimize the distance between the auxiliary parameters in the data and the auxiliary parameters in the simulation, where we average across simulations like we do with simulated method of moments. So this is our objective function, and we have the same weighting matrix that we have in GMM and SMM. It's just now it's a function of these auxiliary model parameters, not the structural model parameters. Some people like this auxiliary model approach because we can link it to common reduced form estimands like treatment effects or difference in differences. And the whole idea is that as long as the structural model is correct, then I should get the same auxiliary parameters in both the data and the simulated model. So if we have the right true value of these structural parameters, then my alpha hat will be approximately equal to my alpha tilde of theta naught. And there's no reason to stop at just 2 auxiliary parameters. We could have many different auxiliary parameters beyond these logit coefficients. We could look at the average mileage at replacement. We could look at some hazard rate as a function of mileage reading. We could look at how long is it between engine replacements. We could include a model with like bus fixed effects, since this is a panel data set. It can be any model we want as our auxiliary model. And we're going to stack all of these auxiliary statistics into one vector. Those are going to be the moments that we're going to match on. As long as it can be computed in both the data and a simulated data set from the structural model, then we're good to go. And the nice thing about this is that we're going to end up simulating the structural model anyway. So why not use that to generate some auxiliary statistics for use in estimation? We don't have to come up with a likelihood function, and we don't have to even correctly specify this auxiliary model. We can use many different auxiliary models. We could have a bunch of regression coefficients from a bunch of different regressions as our auxiliary model. And we can link it intimately with two-stage least squares or diff and diff to clarify where the identification is coming from. So the steps that we would follow is for each candidate value of the structural parameters. For the Rust bus engine problem, we need to solve the dynamic programming problem using the nested fixed point algorithm or some other algorithm, and then use that to use the policy function, which is the policy choice probabilities from that model, to simulate the replacement decisions for n buses and t periods and repeated capital S times. Then we're going to estimate the auxiliary model for each simulation and then take the average across them. So instead of having alpha tilde of theta, we're going to average across the alpha tilde sub s of theta, and then compute the distance and make sure that we minimize that distance. And the larger capital S that we have, the less simulation noise is going to contaminate our estimates. And as with basic econometrics, the larger n that we have is going to improve the precision. So if we have small n, then there's going to be a lot of variability in this alpha tilde s in each one of them. And so that's going to not necessarily cause us problems, but it would inflate our standard errors just like it would in a basic linear regression model. So that is the basics of indirect inference. I hope that you found that insightful and learned something new. In the next video, I'll show you how to implement this in Julia for a very basic structural model, and hopefully that will allow you to cement some of these concepts. Thanks for joining this video, and I'll see you in the next one.